Claudio Dib, SWGO, the Southern Wide Field Gamma Ray Observatory.
Okay, thank you. I'll try to share my screen. Let's see. Okay, can you see the screen?
Yes.
Okay, thank you. So, so I want to tell you about a new observatory of very high energy gamma rays, cosmic gamma rays, that is planned to be built in South America. Oh, I cannot advance here. Oh, there, okay. So first I will describe briefly what it is, this observatory. The science goes, the instrument itself and the site candidates, which is still an issue that is pending. The site is not yet defined. And the timeline, when this be ready and for how long. So what is SWGO, Southern Wide Field Gamma Ray Observatory? Is the next generation of large surface detector array to observe very high energy cosmic gamma rays. So these are gammas that have from 100 GeV to 100 TeV. That's called the very high energy. Then the ultra high energy is above 1 PeV or so. So this will be the first one in the Southern Hemisphere of this kind, and it will be complementary to CTA, which will be built also one part in the North Hemisphere and one part in the Southern Hemisphere. CTA actually will be built in Chile, in the desert, close to the VLT observatory in Paranal. So for gamma rays, we have, depending on the energy of the gammas, usually the more energy the gammas, the less frequently they come, the flux is lower. So for gammas up to like a few tens of GeVs or so, satellites are the optimum. You just get the primary gamma rays detected in space. The gammas never make it all the way to the surface of the Earth, so the satellites are particularly useful. But if you look for higher and higher energies, above 100 GeV gammas, they are not so frequent, so you will need an immense detector in outer space, which is prohibitively expensive. So then you have to find another technique. Well, actually, fortunately, the atmosphere helps like a detector for that. So when you have a gamma coming in the upper atmosphere, it produces a shower, electromagnetic shower, essentially electrons, positrons, and gammas, and they form a cascade. And the electrons and positrons are actually faster than the speed of light in that area, so they produce Cherenkov light. And in addition, the shower also goes down up to a few kilometers of altitude. So the techniques from the Earth there are two techniques. One is to have telescopes that can see the Cherenkov light. And the other one is to have an array of surface detectors on the ground that can catch the electromagnetic particles in the shower. However, as I said, the shower doesn't get too deep in the atmosphere, so you should have this array at rather high altitude. And in the case of the Cherenkov telescopes, there's another issue that the Cherenkov light comes in a very narrow cone of more like a degree or so. So the telescopes really have to look into the direction where the gamma comes from. So if they're looking in another direction, they won't see it. And the field of view of the telescope is like 5 or 8 degrees in the sky, so they don't look in every direction at the same time. So you may miss many of the events. Although the energy resolution of imaging Cherenkov telescopes is quite good. much better than in the case of surface detector arrays. So in that sense, the Cherenkov telescopes and the surface detectors are somehow complementary, in the sense that the telescopes have a good energy resolution, but they have a very narrow field of view. And moreover, you can see the Cherenkov light only at night when there's no moon. So they have a duty cycle that is rather small, like at 15% or so. On the other hand, the surface detectors, they can see the showers all the time. So they have like a 100% duty cycle. And they can see a large part of the sky at the same time, you know, like 45 degrees from the zenith in all directions, at least. But they have a rather poor energy resolution. So these two things are complementary. So the idea is to have these two kinds of observatories to have enough data and accumulate good statistics. So SWGO is actually something that comes up from previous efforts, which is like Milagro, this is in Los Alamos, and HOC in Mexico. I will show you now what they are. Milagro is a multi-institution. Los Alamos Gamma Ray Observatory is actually a pool, like 80 by 60 meters, 8 meters deep, with 2 layers of light detectors, basically photo tubes. One layer is at 1.5 meter below the surface of the water, and the other one is at 5 meters below. The idea is that you can get the electrons and positrons on the top, but they won't make it to the bottom. So when you get signal on the bottom, you know that these are muons. And muons are important because you not only have gamma rays, you also have cosmic rays. Cosmic rays actually is the name of charged particles, essentially protons or nuclei, and they come much more often, like 10,000 times more often than the gammas. So you really need to know how to separate them. So you can separate them by looking at the muon component. So anyway, they did a few discoveries, but they realized that the detector was basically too small in area, so they needed to put some other detectors around. And then they realized that for lower energy gammas, they were really too low in altitude, 2,500 meters above sea level. So they needed to move further up in the atmosphere and also a larger detector. And anyway, they were able, here I show you some things that they were able to find, but still not too many sources, but at least the technique proves to be useful. So now they came with another idea, which is HOC is similar, but now instead of being a pool, these are tanks, rather large tanks, 300 steel tanks, 7.3 meter diameter, 4.5 meter high, and they cover a much larger area. And they have just the phototubes on the bottom looking up. So here they separate the cosmic rays from the gamma rays by looking at, say, the geometry of the shower. So they have some kind of statistical method of separating them, but they don't look specifically at the muons. And well, HOC, which is at more than 4,000 meters above sea level, was able to see more things, of course. They have a catalog of many, many sources in the sky. This is shown here, and what is called the disk of our galaxy. And they found quite a few sources of gammas above 100 TeV, which is very important, this, because it means that these are the gammas that probably come from the places where cosmic rays are accelerated. So now SWGO is a collaboration that was formed based on that experience. But the idea is to go to the southern hemisphere, essentially because the center of our galaxy is seen from the southern hemisphere. And in addition, they look for a place that is higher, above 4.5 kilometers altitude, and of course larger. In addition, they want to have muon tying capability, essentially like these 2 layers of detectors, so you can actually tell immediately if you have lots of muons, this is a cosmic ray and not a gamma, and so forth, you can separate them. So the collaboration formally was established about 1.5 years ago. So it's quite new. There's a lot of progress done, many countries all around the world. And here you can see a map of the geographic locations of the gamma ray observatories. Of course, most of them are in the Northern Hemisphere. In the Southern Hemisphere, there are, well, HES particularly is in Namibia. This is a Cherenkov telescope array of like five telescopes, 4 medium-sized and 1 large. And from here is the experience of building CTA, which is a much larger array. CTA have 100 telescopes of 3 different sizes in the Southern Hemisphere, and in the North also with a relatively lower number, I don't remember, like 25 telescopes, and of large and medium size. So it would be ideal to have a complementary surface array detector in the Southern Hemisphere. So the proposal is to have something here somewhere in the high mountains in the Andes in the Southern Hemisphere. The science that we're looking for is, well, first of all, with a detector that can have a 100% duty cycle, you can detect transient phenomena quite well, and you can also use this as a trigger for CTA, for example, because CTA will not be able to see easily unless they're looking in the direction already. They will not be able to see short events in time. So SWGO can inform it, and then they can tell CTA to look for more details. Also, you can search for pevatrons are regions where you have the production of very high, ultra high energy cosmic rays. So these are regions in the cosmos where you have accelerators. The pulsar wind nebulae and halos are also some extended sources, which for a wide field of view detector is ideal. Dark matter, of course, is also a very important issue, particularly close to the galactic center. This is an important thing, and also in the halo of the galaxy. And in addition, you can also study cosmic rays. Well, Pierre Roger studies ultra high energy cosmic rays. So cosmics of 10 to the 18 electron volts or so. SWGO will have a lower range of energy, up to 100 TeV or so. So very high energy, which is close to the so-called the knee of the spectrum of the cosmic rays, where it's important to study there the composition. You want to know, very well if these are protons or other kinds of nuclei or so on and so on. So this will help. In addition, having this kind of detector in the south, you could study in more detail the anisotropies that the cosmic rays have. So here, there's an interesting issue in our own galaxy, which is the Fermi bubbles, which are kind of regions away from the plane of the galaxy, basically in the halo, where there is a lot of very high energy gamma rays coming from. This may be remains of the possible active nucleus that our galaxy had. So there were jets coming through here, and not anymore. So they left these kind of clouds there. It's an issue that is interesting to study. Well, for the dark matter, annihilation and decay, or WIMPs, thermal WIMPs, relics, is something that can be studied, and maybe can discover, it depends, well, we really don't know what mass WIMPs could have, and we don't even know the profile they would have in the galaxy. So there are different models that study this, but one can put bounds on this. So at least this would be a lot of knowledge we can extract from this. And well, there's a whole list here of sources of gamma rays one can study. Don't want to go into too much detail, you know. From the point of view of our own galaxy, I already mentioned some. Then extragalactic, of course, you have satellite galaxies to the Milky Way, radio galaxies, quasars, blazars, gamma ray bursts, etc. Now, so to accomplish this, the concept of the observatory will be, as I said, a high altitude particle detector above 4.4 kilometers above the sea level, in the latitude range where you can see the center of the galaxy, so like between 15 and 30 degrees south, closer to 30 degrees is better. With a detector has to be large enough to catch a wide range of energies. Here is that if you want to detect lower energies, you need to be way above. And if you want to detect high energies, you have to have a large detector because you need to cover a large area because the flux is lower. So you have these two things playing one against each other. And the high fill factor means that you don't want to have too many open spaces in between the water detectors because you want to cover very well, at least in some area of the space, so you can see the lower gammas, as I show you immediately here in this picture. So here you see this kind of purple is the Hawk. It's at 20,000 square meters. And the idea is to have a much larger core array and with a higher fill factor, fewer holes in between. This is to catch the lower gammas. As you see, for example, here, this is a 200 GeV gamma, and this is a 2 TeV gamma, so one order of magnitude larger, and you can see that you have much more signal here than there. So you really want to have a lot of detectors, very concentrated to catch this. And then the rest of the array outside is more sparse to have coverage for a larger detector for lower fluxes, which is a high energy. This curve here, this shows the profiles of how the shower is decaying as you go deep into the atmosphere. So here on the top, I show the kilometers above sea level. And you see that for 100 TeV, well, you have lots of particles anyway, but they don't come too often. But for like 100 GeV, the shower starts decaying very quickly. So if you are at 4,000 meters, you get much less than at 5,000 meters, for example. So this is important. Now the concept of the detectors is, well, depends on where you build it. One idea is to have tanks. If you are building in the desert, you will have tanks and with water inside. The detection technique is that when you have a charged particle going through the water, will create a chunk of light that you catch it inside the detector. That's a simple idea. And you have two layers, one layer on top and on the bottom, so you can see if there are electrons and positrons or muons, essentially. You can separate them. Now, if you're in a lake, well, you have to have a different kind of configuration, similar concept of detector, but you have to have another array, or you can have a pond. And so there are these three kind of detectors that are being studied because we don't know yet where we will place this. These are the candidate places. There are some places in Peru, in Argentina, in Chile, and Bolivia. You can see here, the Peruvian sites are a bit further north. The Chilean and Argentinian sites are a bit further south. Here, Chile and Argentina, well, the Chilean side is close to where Alma is. It's actually in the same plateau, the Chacnantor plateau. And in Argentina, it's in Alto Tocomar, this is where Llama and Cubic are there. So this is something that is still being studied. We have to still find what's the best option, and this program should be resolved at the end of this year. So this is like the timetable. You will see that by the end of 2022, this will be operated, probably not full size, but we'll start the operations already. And it's expected to work for about 15 years, taking data. So, from conclusions is that, well, there's a strong motivation for a wide field of view, high duty cycle gamma ray observatory in the Southern Hemisphere. This will be complementary to CTA. It will be able to detect hard spectrum sources, especially transient and multi-messenger phenomena will be very important to study. Extended sources, because of the wide field of view, is also useful in this case. And in addition, LASO is a similar observatory in China, in the Northern Hemisphere, and HAWK in Mexico. These will also be good places to do joint studies of the full sky. It's a great opportunity for collaboration of our community in science and also in the technology. So thank you, that's my presentation.
Okay, thank you, Claudio. Other questions? No. A question? I don't see. Marcelo, please.
Yes, thank you, Claudio. You mentioned that there were parts in the sky or in the universe where accelerators are there. So you produce this, I don't know, hundreds of TeV gamma rays.
Right.
Can you say something about these accelerators in the universe?
Well, I mean, the most obvious thing that you can think of, a place where you would have cosmic rays of, ultra high energy, like, 10 to the 15 electron volts or so, is supernova remnants. The explosions will create this shock wave that accelerate the particles, and then these particles will collide also and radiate, and then you will have the gammas, also of a very high energy. And this is like the main idea. But of course, the main thing is that this is, it's like research. You will find also probably things that you didn't expect. So this is something that we have to keep an eye on.
Thank you. Thank you.